Okay. So, all right, so we're going to, excuse me, we're going to switch gears now. It's all right. They can come to the lecture, I don't care. All right. All right, so the last 4 lectures, we're going to be talking about membrane, structure, and function. All right, so today we're going to start off just like we did with proteins. We started out with the building blocks of proteins, understanding their structure so that then we could see how they come together and then how the things can function. Same general approach here. So we'll start to talk about lipids, biological lipids, and the constituents of biomembranes. So fatty acids, which are really the smallest building blocks, so you don't really see fatty acids as free fatty acids in membranes, but they're the precursors to the major component of the membranes, glycerophospholipids, sphingolipids. We'll talk about cholesterol, and then having a feel for some of those structures and properties, how the lipids come together through a self-assembly, and we get membrane structures. Okay. So just a depiction so you know, if you don't already, where we're going. Over here is a membrane bilayer, and we'll talk more about that as to how you get that structure. Ultimately, we're going to want to know not only how the membranes are formed, but what the properties of these are. All right? When you think about biological membranes, the biological membranes aren't just a permeability barrier, right? They're impregnated with proteins throughout that will traverse the membrane, and they're going to be important for moving things from the outside of the cell inside, outside, and those will be both substances as well as signals, all right? So once we understand membrane structure, we then want to understand the properties, and we'll see next week how the composition of these membranes, right, the types of lipids that are there are going to dictate how fluid that membrane is, all right? Whether it's a relatively rigid membrane or whether it's more fluid, because these proteins, the receptors, they're embedded in there and they're going to be moving around, all right? So we'll see examples of how not only appreciating the structure of the membrane, but the composition of the membrane is going to determine its properties with respect to fluidity, and that's going to reflect the ability of proteins to be moving around, like RAS in a C, to do what they have to do in the cells, all right? So ultimately, we're going to be looking at that. Okay, so you'll see that the lipid structures are obviously not amino acids, but you should question and then see, yes, in fact, there are common features to both the building blocks of membranes and the building blocks of proteins, all right? So start with some definitions. What do we mean when we say a lipid? In this case, we're talking about a biological lipid. So a biological lipid is any substance that's soluble in a non-polar solvent and is sparingly soluble in water, right? It'll, much like we would say a hydrophobic amino acid, but with some important differences. Even though the biological lipids are largely hydrophobic, the main thing to take away, at least today, in terms of what is really driving most of their assembly into higher order structure is that they're amphipathic, all right? That different parts of the molecule have different properties, and that is one of the most, if not the most important feature of biological lipids, is that they're amphipathic, okay? So we're not going to get into the physiology of hormones and the biosynthesis. You'll get that later in the class. But steroid hormones, cholesterol is precursor to that, so that's important. We'll talk briefly about the fact that cholesterol is the precursor to bile acids or bile salts playing a role in digestion. Fat we'll talk a little bit about in terms of the breakdown next week, both in terms of energy and tastiness, right? But today, this is really what we're going to be concentrating on, which are the major components of biomembranes and how they come together. Okay, so when I tell you the initial building block is a fatty acid, bless you, that sounded wet. A fatty acid, even as I say fatty acid, that's almost an amphipathic statement, right? Fatty acid. So the fatty part comes from a long chain carboxylic acid. The number of carbons in there ranges from about 12 to 24. So this is the hydrophobic fatty part. The acid part is this carboxylate group up here, all right? So we have a polar head and a nonpolar tail on a fatty acid. When you look at different fatty acids, all right, the acid group is the same, but there are two other features that distinguish fatty acids from one another. One would be the number of carbons in the chain, and the second is the degree to which that carbon chain is either saturated with hydrogen, i.e. no double bonds, or it is unsaturated. Unsaturated means you have double bonds in there. And by and large, when we're talking about these fatty acids, when you have an unsaturated fatty acid, most of the time, it is in the cis configuration. So what do we mean by the cis configuration? The hydrogens are on one side, and the flanking carbons are on the other side. So when you look at that, and you look at the space filling model, what does unsaturation in the fatty acid do to the structure of the tail? It's a bend or a kink. So we're going to see how when these ultimate glycerophospholipids, which we'll get to in a minute, as they're coming together, the ability to get nice and close and to pack, that's going to be influenced by the composition of those fatty acid tails. Because if they are saturated, they're going to be able to come very close. You should think ahead about this. But if you have a lot of unsaturated fatty acids, with those bends, they're not going to be able to pack quite as much. And what might you anticipate that that's going to do with respect to the structure and function of the membranes? It's going to change it, right? Question? Yes, because I took a different picture here than what was in the notes, and I'll tell you why there's a difference. So first of all, what do we mean by this? The nomenclature is that, I didn't change this, the nomenclature is that you have 18 carbons in the chain. So that by itself designates that as linoleic acid. Now, the degree of saturation that you would have in a linoleic acid chain can vary, right? In some cases, you can have 2 double bonds. In some cases, you can have 3. So in this case, how many double bonds do we have? As so was adroitly pointed out, I have a typo here because I took this from the notes, which this structure here, I flip-flopped, and I didn't change it in the notes. This number here would tell you how many double bonds are there. So this number here, in looking at this structure, it wasn't that bad of a typo. You didn't That number there should be what? 2, okay? Now, in subscript, this is telling you C for cis, i.e. reminding you that it's a cis double bond, but invariably it is. And then delta 9, 12, that's telling you the position. So this nomenclature says if you have a fatty acid, the first number tells you how many number of carbons there, that tells you what type it is. The second number after the colon will tell you how many double bonds are there. For palmitic acid, 16 carbons, no double bonds, so you know it's saturated. Here, if this is 2, you say, well, where are the double bonds? The first number, 9, means the double bond is involving carbon 9, but how do you number the carbons and which way is it going? The first carbon is here from the carboxylic acid group. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 9th carbon is the one that there's a double bond, and it's always moving forward. So if you say number 9 there, you know the double bond is between 9 and 10. So there's 9, 10, 11, 12, and you pick up the second designation between 12 and 13, okay? So fatty acids, they are amphipathic, their name is amphipathic, and know your designations without typos and what that implies in terms of the structure, all right? Okay, so fatty acids are not by themselves in biomembranes. They are part of, and they are attached to other carriers. So in the first case, this is the major constituent of biomembranes, which are glycerophospholipids. So the glycero, where does that come from? The backbone of these biological lipids is glycerol. So you have 3 carbons and 3 hydroxyl groups. So if you flip that over here, we've got number 1 carbon, number 2 carbon, and number 3 carbon. So on the first 2 carbons, all right, you have ester linkages, and ester, I can't get that out of my mind. So if this was a fatty acid tail, what? I don't know. It's, yeah, I'm sorry. If this was an acid group, initially as a fatty acid, right, the acid group comes together with the hydroxyl, right? You get elimination of water and an ester bond. So these ester bonds are linking up a fatty acid to carbon number 1, another fatty acid to carbon number 2, okay, of that 3-carbon glycerol backbone. The third hydroxyl group here on carbon number 3, that gets a different, what? Okay. Oh, all right, sorry. No. Here? 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 Oh, all right. Hey, man. I'm not perfect. My ex would tell you. Okay, so what are we doing here? These 2 fatty acids are being added to glycerol. And the third hydroxyl, this is a phosphodiester, right? It's a diester linkage and phosphorus in the middle. And then up here, okay, is what we call the head group. All right, so this entire entity here is a polar head group. So you have a phosphodiester linkage to something up here, which is polar, and this is going to vary, and we'll see this in a minute, okay? So what you're doing here is we've got a hydrophilic head, which is coming from this head group, and we have a hydrophobic portion, which are these fatty acid tails. So much like a fatty acid itself was amphipathic, its polar group was what? On a free fatty acid. Not a phosphate. The acid group, right? The acid groups now have been sequestered into the ester linkages. So we're losing polarity there, but we're gaining polarity here. Why? This group is going to be charged, and it's going to vary in the different types of glycerophospholipids, but look at this, okay, that phosphodiester. So what you're doing is you're taking two fatty acids and bringing them together, but to maintain the amphipathic nature that you really need, as you'll see here for these membranes, we've now added something that is very polar. Right? So these glycerophospholipids are, in fact, more polar than their fatty acids, right? The corresponding fatty acids. Okay, so we're going to look at some different glycerophospholipids, and you have to think about this in a couple of ways. First of all, there's a limited number of polar head groups that can be put on here. So if you put a particular head group here, what, if anything, would that have to do with the hydrophobic tails, the fatty acid tails that were put there? i.e., we can have a given distinct head group, but the fatty acids that are here are going to vary, right? They're going to vary in length, right? They're going to vary in their degree of saturation. So when we talk about a glycerophospholipid, let's not worry about phosphatidic acid. That is the precursor to all of these. So look at this. You're going to have to flip it a little bit. Like take this guy and flip it first on the horizontal. Here's carbon 1 tail, carbon 2 tail, head group. Carbon 1, even though this is, carbon 1, and this is R group 1, 2, and 3, okay? So let's look first at, someone would say, I'm looking at the glycerophospholipid phosphatidylethynolamine. Ethanolamine, because here after the phosphodiester, what do we have here? Ethanolamine, right? So that's the head group, the polar head group. But when we say phosphatidylethanolamine, we're talking about a family of molecules, right? It's a family of molecules. What they have in common is they are glycerophospholipids, i.e. the backbone was glycerol, it's phospho, it's a lipid. The ethanolamine is designating the head group, but these R groups can vary and do vary. So phosphatidylethanolamine is a family of glycerophospholipids that have a common structure, but the nature of the individual fatty acids that are hooked up at position C1 and C2 vary, right? Phosphatidylcholine, a major component of biomembranes, same thing, but the R group is different. This is choline. Phosphatidylserine, the amino acid serine. Phosphatidylinositol, okay, a large ring structure, all right? So I'll give you a warning of where we're going with this, which we're going to get into Monday. It's not a warning like don't come to class. It's a heads up. Do these structures vary? They do. Their basic structure is the same. The structure is giving us a lot of permutations and possibilities for the composition and nature of the hydrophobic tails, right? They can be straight, they can be bent, they can be long, they can be short. And when we start to think about how they come to pack, right, longer tails might give us better van der Waals. More bents, they're not going to come as close together. And then the head groups also vary. They all have to be polar, but they vary in terms of being rather simple as opposed to big head groups. So where we're going to go with this is that with all of these possible families to come together and all of the variability that you can have, you can have biomembranes that have very different functional properties because they're comprised of these families that have variability, all right? So this you're going to have to memorize for the second exam, all right? I'm not... No. So the main thing here is to look at this. Everybody's ears go. The main thing here is to appreciate the fact that when you look at the membrane composition of different cells, right, or different membranes within a cell, that it's not one flavor, right? When you look, let's say, at the mitochondrial membrane, right, you've got a lot of phosphatidylcholine, ethanolamine in it. You don't really have any sphingomyelin, which we'll get to in a second, whereas in other cells, right, what this underscores is that different membranes, either within the different compartments within a cell or the different cell types, they have different functions. And they have different functions, they have different proteins in the membranes to give them the functions that the cell is trying to achieve, and that those alterations in the properties of the membranes and the resulting proteins that are in the membranes, right, that can vary, and it does vary, but you have to have a structural basis for a functional difference, okay? Okay, so let's move on to the second class. So the second class are sphingolipids. Now they are different from the glycerophospholipids. First of all, their backbone is different. They do not have glycerol as a backbone. This is the backbone, sphingosine, which is, okay, a long-chain fatty acid. No, it's not a long-chain fatty acid. It's a long-chain fatty alcohol here. So the first thing is this is going to be common to all of the different sphingolipids. We're going to bring in another fatty acid now, but we're not going to hook it up in an ester link. They're not going to answer it? Get out of class. So we're bringing another fatty acid in here, right? Here's the fatty part. The acid part has the carboxylic acid group up here. So now this is getting hooked up to the backbone, not by an ester link like we saw with glycerol, but with an amide link here. So this is the backbone, sphingosine. So now we have a ceramide, which is this fatty acid is going to be constant in all of the sphingolipids because that's part of the backbone. So here we're bringing in a fatty acid, and obviously that can vary. Now, when you think about the head group, okay, there are different types of head groups, but for our purposes, the major sphingolipid, all right, the head group is choline. And so that gives us single myelin, okay? Now, if you look here, this single myelin, is it another mistake? Say what? The circle means that I was showing the polar end of it, and I didn't do it in the notes. I had made this slide, and last night I was thinking about erasing it because I figured it's going to draw someone's attention, and I don't need, right? And I just said, no, okay, don't worry about it. Here's the polar, here's the nonpolar. God, you guys are feisty today. Okay. Is what always like what? For the single lipids, the backbone is always sphingosine. So one of the long hydrocarbon tails is always the same. Okay? Just one circle. That's a bracket. Okay. At this point, you can also add head groups that are sugars. All right? They don't contain phosphate. They can be relatively simple sugars, which is called gangliosides, or cerebrosides that are complex. All right? We're not going to get into those structures and those functions. The major one is, in fact, sphingomyelin, and that is a phospholipid, okay? Because of that phosphodiester link to choline. All right, so when you look at sphingomyelin, which is the major single lipid that's in membranes, you should be able to see that even though it's in a different class of biological lipid, it looks a lot like phosphatidylcholine. First of all, the choline head groups are the same. They're both hooked up to their remainder of the molecule by a phosphodiester, right? Let's look at phosphatidylcholine. Phosphatidylcholine, what is the backbone? Glycerol. So one of the carbons here, there's an ester link, here an ester link, here a phosphodiester link off those three hydroxyls. You've got two different fatty acids here. And remember, when we say phosphatidylcholine, PC, or sphingomyelin, are we talking about a single molecule? No. We're talking about a family of molecules in that the nature of these two fatty acid tails can vary. But this is going to be the same, so that's a family. So this family, what do they have in common with this family? The head groups are the same. The phosphodiester is the same. The linkages in here are a little bit different, but they both have two tails. The difference here is one of the tails is always going to be the same from sphingosine, but the other one can vary. So in fact, when you look at the space-filling model in terms of the polar head group being a phosphodiester hooked up to a choline head group, right, and then having these two tails, even though their linkages are a little bit different, their three-dimensional structures can be quite similar, then you'll see that, in fact, sphingomyelin and phosphatidylcholine, even though they're two different types of biological lipids, that they look the same. And so if they look the same and structurally they're very similar, you would anticipate that they're somewhat interchangeable in terms of their representation in membranes. They are, to large part. Okay, so the third major component in biological membranes is cholesterol. So structure dictating function. This is just three different views of it. The important thing is that the core is this rigid steroid nucleus, this rigid ringed structure, all right? So this can go off to make hormones, but this rigid structure here, if you think about where we're going, the amount of cholesterol in different membranes can vary. So if we're ultimately trying to understand even the function of membranes and the fluidity and the ability of proteins to traverse through and signal and so forth, the more cholesterol you have in there, right, if this is a real rigid molecule, it's going to have an effect on the fluidity of membranes. This is a steroid ring. The nucleus meaning this is a steroid ring, and then this is a tail, right? So there is a little hydrocarbon tail here, and when you look at this, the sole polar contribution, remember we said that all biological lipids, and cholesterol is one of them, are amphipathic in nature. This guy is just getting in there in terms of having amphipathic properties because of this hydroxyl group here, okay? So hydroxyl here, there's a polar end, but the rest of it is very hydrophobic and very rigid, all right? So we'll see how it gets incorporated into membranes and what effects it has on the membrane dynamics. We won't talk about, obviously, hormone biosynthesis because that's not part of the class. We'll talk on this just briefly, i.e. now. So cholesterol, if you look at it, let's back up. So here is a side view of these ring structures. And when you look, it's polar here, and these methyl groups are all pointed in one direction, and these hydrogens are in the other direction, all right? Now, if you take this, if you take cholesterol, and in this depiction, okay, the methyl groups are pointing up, and the hydrogens are pointing down. I mean, you could flip it, it really wouldn't matter. This cholesterol, is it amphipathic? It is, but it's kind of marginal. So if you take cholesterol and you modify it, you get bile acids or bile salts, which I'm sure some of you have experienced if you spent too much time down at the steer. Right? The steer. If you don't get it, that's probably a good thing. So, bile acids, they assist in what? Digestion. We'll see that a little bit better on Monday, I think. But if we take cholesterol to get bile acids, we are going to modify it by putting hydroxyl groups on and by putting a carboxylate on it. So the carboxylate is here, and when you look at these hydroxyls, they're all being put on the same side of the ring structure. So in this case, they're all being put down. So now what have you done in terms of making that more polar or less polar? You've made it more polar, and the polar groups that you've added are on one side, primarily on one side of the ring structure. So here, where you had these methyls and the hydrogens, right, the methyls are now still there, but now you have a lot more polarity on the underside of that ring, and you have a carboxylate. Right? So if you look at the structure of a bile salt, it should almost make you think of a detergent, which in fact is what it is in a way. All right, so we'll look at that more on Monday. Okay. So if you remember on lecture 1, we had the example of if you have water and we start to add in a non-polar molecule like methane, what happens? So let's back up now, and in thinking about membranes, let's say we start with water and we're starting to put in glycerophospholipids or singamidin. So we're going to call that the monomers. As we put them in, okay, they are in fact amphipathic, but by and large they have a lot of their nature being hydrophobic. So they do have a portion of the molecule that can interact favorably with water, but a lot of the molecule that can't. So as you start adding more and more of it in, the water molecules that are there, as they see this stuff coming in, what's their response? Do they become more ordered or less ordered? More ordered, right? There's a lot of hydrophobic nature coming in. So you get to a point in the normal hydrophobic effect that we said that as you're adding more and more and more, there's an entropy-driven process of self-association, and the driving force for that is increased entropy of the water molecules. And so that is, in fact, the major driving force for the establishment of biomembranes. Right? First of all, if you have, as you're adding this in, some of it, right, some of these phospholipids could give you a monolayer on top, right? The polar head groups are going to interact with the water. That's good. And they stick their tails up in the air away from the water. Water says, you want to sit on me, that's okay. I'll interact favorably with your head group, but project your tails away from me. You don't like that. All right? If you look at it, you should see why that is favorable. All right? If they were the other way around, it wouldn't be favorable. So a second way that you could get this self-association would be to form a micelle like this. So the micelle would be a sphere where all of the tails are projecting in and all of the polar head groups are on the side, all right, on the periphery. That would make sense in terms of the sequestration of the hydrophobic tails. The degree to which you can really efficiently do that is going to be largely dependent on the nature of these phospholipids. If the tails are too big, too long, right, or maybe too many bends, then you're not going to get it packing into a nice, tight micelle, right? What we're mostly interested in is a bilayer. So here, this is a three-dimensional bilayer. Here, you're simply looking and seeing how it is that they come together. So in this case, we have one leaflet. So a leaflet here, all of these tails are nestling next to each other. All the polar head groups are towards the solvent, and then the other leaflet of the bilayer. Right? So this is showing it to you in terms of a sheet, but this is really what we're talking about with respect to a cell or an organelle, where we're getting two aqueous environments on the outside and the inside, and they're separated by that bilayer. What's driving this? Number one, the most important, is the hydrophobic effect. But we also have, we've got van der Waals between these tails, and we have favorable enthalpy between the polar head groups and the solvent. Okay? Now, just to jump ahead before we're done, think about, even before you read the notes, think about the fact that we said that these lipids, the tails, can vary. They can vary in their length. They can vary as to whether they're straight or kinked. And cholesterol can be put in that's rigid. So just as a mental exercise, if you're so inclined, try to anticipate the composition of these membranes in terms of, let's say, van der Waals. If you have a lot of van der Waals interactions, then that might make that membrane more or less fluid. Less fluid, right? So jump ahead and just try to think, if I look at membrane 1 versus membrane 2, and I wanted to make this membrane more fluid than this, how could I do it? Right? Think about changing the length of the fatty acid tail. What's that going to do? The degree of saturation in double bonds, what's that going to do? The size of the head groups, what's that going to do? All right, and we'll get more into detail of that on Monday. Test scores will be emailed to you very soon. The last makeup exam I'm giving will be in 15 minutes, so before noon. That'll be done. Early afternoon, the exam key will be posted outside the biochem office, and you should get your grades before then by email from the grading center. Okay? See you on Monday. I will post problem set 4 on the weekend. Problem set 4 is going to cover the last 4 lectures, today being the first of the 4.
And so in recitation, we're going to finish going over problems